This is Chapter 8, Problem 42. Here we have a worker pushing a 27 kilogram block a distance of 9.2 meters along a level floor at a constant speed with a force directed 32 degrees below the horizontal. Right away we have to realize that the worker is being incredibly stupid because he's pushing down on the block instead of pushing up, so he's increasing the normal force. That force is going to be equal to F multiplied by the cosine of theta. That's the x component of the force, and then the y component of the force is F times the sine of theta. Okay? On my free body diagram, we have mg plus Fy acting down, and then we're going to have the normal force acting up. We need the normal force to find the friction, and then we have Fx to the right, and then opposing that motion is the friction force. Since the block is being pushed with a constant speed, that means that Fx is equal to the frictional force. So I'm going to put that right down here. Fx is equal to the friction. That means that F times the cosine of 32 is equal to, the friction force is going to be 0.2, that's our coefficient of friction, multiplied by the mg, in this case that's 27 times 9.8, plus Fy, which is going to be F sine, running out of space, of 32. F sine of 32. Sorry about running out of space there. And now we're going to solve this for the force. So we have Fx is equal to the force of friction, F cosine of 32 is equal to 0.2 coefficient of friction, multiplied by the mass times the gravity constant, 27 times 9.8, plus the F sine of theta because he is pushing down. After all that math, you should get a force equal to 71 newtons, which means that the x component of the force, Fx, is equal to 71 multiplied by the cosine of 32. It's the x component of the force. So in order to find the work done by the worker, we're going to multiply F dot d, that's going to be the work done, F dot d is equal to the work, and that's the force in the direction of the displacement. You could use the dot product. You'll see that there's no displacement along y if you use the dot product. Or, since you already know Fx in the direction of dx, it's just going to be 71 cosine 32 multiplied by the distance traveled, which is 9.2 meters. And you get a work done by the worker equal to 553.95 joules. The work done by friction, or the change in thermal energy, remember how I talked in class that the book can use several different terms for the work done by friction. That's going to be equal and opposite in order to make sure that the box is moving with a constant velocity. There's no net work done to change the kinetic energy. We can also calculate that work done by friction directly. So the work done by friction would be equal to the frictional force multiplied by the displacement, and the cosine of the angle would be 180. The force is to the left, but the box is displacing to the right according to our original picture. So that's going to be equal to 0.2 multiplied by the mg cosine theta, 27 times 9.8, plus the 71 times the sine of 32, as my cat jumps right behind my head. Not that I'm trying to get any work done here, Mickey. And then you multiply that by the displacement, which is 9.2. Okay? So 0.2 times 27 times 9.8 plus 71 times the sine of 32, and then you're multiplying that whole thing by the displacement of 9.2, and you should get something that is roughly equal to the work done by the person, 553.95 joules.